Welcome back. In this video, we'll be looking at finding stationary points of a function and determining their nature. More precisely, determining their nature means that determining whether the turning point is a maximum or a minimum. That is, either it's a local maximum or a local minimum. Now, you might be thinking, what's the difference? Why am I using the word local here? What does it mean to be a local maximum, local minimum? So let me show you on a graph. We already have learned about the stationary points. Where I said the gradient is equal to zero. So we briefly looked at that before we went to determine the interval of increasing and decreasing functions, remember? Now, we're calling this turning point a local maximum. The, the difference between local and global, they're not the same thing, okay? There is a word global. You are sure nowhere else on this graph you have a maximum. For example, if you have a negative quadratic, you have negative x squared, you are sure that that turning point is a global maximum. Now, we are not saying this point is the global maximum because obviously the y value here is higher than here. We're saying around this region, in this neighborhood, in this locality, is a maximum point there. Okay, so obviously this is higher. Yes, actually we're using y values, so a higher point means it's more often it has a higher value. So, and this is a local minimum because it's around this neighborhood, it's the most lowest value. Okay, so that's why we use the word local, and now we're gonna get to the meat of the matter. So let me get rid of those. There is also a point here where the gradient is briefly zero, and also we call that the inflection point. Now, inflection points are not highly examinable and they're not used much in AS so don't worry about too much about those. The point is that at each of these turning points, the gradient, at local maximum, the gradient is zero, and at local minimum, also the gradient is zero. So we have to find a way to distinguish between those 2 points there. So how can we distinguish between the maximum and minimum turning points? Now, I've put these graphs here for you, so you see that the gradient is positive to the left of a maximum and negative. So, if you think about the numbers here, the gradient is positive number is zero, and then it turns into a negative number. So the gradient, the f dash is actually f dash, its change is f double dash, and that this f double dash is telling us that will be negative because there is a decreasing was positive first, and then it turned into a negative value here. So f double dash test, there is a point actually to it. So f double dash, we evaluate it at the turning point, and if f double dash is negative, actually we conclude that this is a maximum. All right. So here function is a negative number to the left, then it turns into zero, and then into a positive number. So these are the f dash. Okay, the f dash will give you this sequence here, and the fact that this sequence is increasing is found by f double dash. Now it becomes clear when I use an example for you. This is an increasing sequence, and that's why f double dash will be positive. So whenever f double dash is positive, second derivative is positive, is actually associated with a minimum. It's somewhat counterintuitive because how can a positive number the minimum, and because it's measuring the rate of change, not the initial rate of change, but the rate of change. All right, so or rather, the rate of change of the gradient is positive. Okay, so it's written down there. So here, this f double dash equation, it gives us the equation of the rate of change of the gradient. Okay, so when I'm repeating the rate of rate, that means the rate of change of rate. Okay, so let's see in more, uh, maybe this graph will help you consolidate what I just said, because we are evaluating around the maximum the gradient one more time. It's a positive number to the left, becomes zero at the turning point, and then it turns to a negative number. Think of this as a sequence. If I told you plus 3, 0, and then minus 5, and I said, is this increasing or decreasing? You say it's decreasing, and that's found by f double dash. Okay, so, and it's the opposite around the minimum. First it's negative to the left of it, it's 0, and positive to the right of it. We read numbers always from left to right, okay? We evaluating these sequences from left to right. At the beginning of the lecture, if you remember, we had those, we read the numbers from left to right. This as we assuming that we are reading the sequence from left to right. Alright, that's why f double dash will read positive. Okay, so now we see an example which should consolidate what I just said. So, and also, okay, this is not an example, my bad. This is just another thing to say that at inflection points you might have a negative gradient, it turns into zero, and then it turns into negative again. So these are the points of inflection, and there's another case of point of inflection. This is not a turning point, so if you been given a sequence of you have been given a sequence of gradient functions that turn into, for example, positive and then zero and then positive again. They are not turning points really. Okay, so with that in mind, we're gonna solve this example finally. Okay, so the function is x to the power of 4, and we are and subtracting 32x from it. State whether it's the turning point. First of all, we have to find the turning point, and then we're gonna classify it with either of these rules. Okay, so first we find the first derivative and we set it equal to 0 and solve this equation to find the x coordinate in the first place. So solving that, we will get x is 2. Then what we do is we look at the derivative function and we differentiate it one more time. We are, well, yeah, you didn't have to. We are just finding the y value here, okay? That's just saying the y value. We are differentiating this derivative function one more time. So this term here gives us this, and the 32 simply goes to 0. Don't need to write anything for constant. So now what do we do with this second derivative? We actually use this point that we found x value for the turning point. Remember, this is where we set the derivative function equal to 0 and solved it to find the turning point. So we substitute that into this expression and we want to know whether it's positive or negative. Here is the moment of truth. So 12 times 2 to the power of 2 is certainly positive. So we have, voila, this case here where f double dash is positive. Therefore, it's a minimum. Okay, so just remember the shape of those three lines there should make you remember this is a minimum. Okay, then that's enough for us to conclude that the turning point is the minimum. Is there another turning point? Not really, because the only turning point of this graph is at x equals to 2 and y is minus 48. So let's look at another example. In this question, we've been told to find the stationary point on the curve and state whether it's a minima or maxima or point of inflection. So minima means local minimum and local maximum is maxima. Okay, this is just another way of saying it. So let's find the first derivative here and we're going to get these values. Now setting this f dash equal to 0 is certainly going to give us two roots to this equation, so there will be two turning points, certainly two turning points. So x is 4 and 1. These are where the gradient function becomes 0. Now, first of all, we're finding the y values with substituting them into the original formula. We just putting them back into this function to figure out what y is. Y's are going to come out to be 17 and minus 10. Then we are going to differentiate the first derivative one more time to get the f double dash. So second order derivative. Here's a moment to truth. When you substitute 4 into it, we're gonna evaluate it twice. Okay, so first we substitute 1 into it, we're gonna get the negative value of 18. So we saying that it actually is like so. We had a positive and it turned to 0 and then it turned to a negative value. So the minus set number is the important part. We don't care about its absolute value, we just concerned with this sign, okay? Sign is negative. So then we are concluding that it's maximum. It's just the rule that you have to remember that when you have a negative sign, it's maximum because this sequence is decreasing. Alright, and now we're going to evaluate the 12x minus 30 at point x being 4 and we are going to get positive 18. Therefore, we have a minimum. What does that mean? It means that we have this sequence there. We have the negative and then a zero gradient and then a positive gradient. So this was a f dash and it's this sequence is telling us it's increasing. Okay, it's an increasing sequence and is coming from the sign of this number here, not its absolute value. We don't care, could have been plus 1. All we care about is whether it's positive or negative. What's important is the sign of the f double dash. Alright, so let's look at this example. We've been given this quark cube and we are finding the maximum and minimum. Is this the same equation? Yes, it's still the same equation and it's the same working out. Okay, so just to conclude, there is yet another point about this. There is a point of inflection. We said, alright, this is summarizing what we said earlier. Remember this. Alright, so it's because it's counterintuitive. Then f double dash evaluates to a negative value, it's actually maximum. So alright, so that was the last example. The point of inflection is less we ask, but when if in at any point f double dash turns into 0 is actually telling us that some points where f of x, well, f dash of x equals to 0 and f double dash of and if this happens, then that means that we are looking at point of inflection. Now you might be thinking, you told me point of inflection was something like that or something like that. Well, this is yet another kind of point of inflection. You learn about it in year 13 where this concave graph is turning into convex graph and there must be a certain point where the f double dash is 0, because all along this region f double dash is always, what is it? Is it positive or negative? Is negative, alright? So if f double dash is less than 0 and here f double dash is positive, is greater than 0, there must be somewhere where the sign changes, alright? And that's the point where f double dash is 0, remember? So there must be a sign change at some along this x values. So I'll see you in the next video.